Hi, my name is Richard. This is Eric. And we're going to be talking about scalable reinforcement learning with RLLib. This is a project that has been in the works for the last year from the Ray RLLib at UC Berkeley. So a quick overview of today's talk. We'll start with the primer on reinforcement learning, which is an exciting new technology with broad applications and then motivate its need to scale up. We'll then talk about Ray, which is a distributed execution environment we've built in the Ray RLLib targeting emerging AI workloads. And finally, we'll dive into RLLib, which is an optimized, scalable reinforcement learning library targeted at both researchers and practitioners, and also discuss its abstractions for reinforcement learning. So what is reinforcement learning? To start off, reinforcement learning is centered around interaction. We can take, for example, an advertising system. So this thing on the left is an agent, and we'll have it serve video ads. The ad system interacts with users, and we'll call that an environment. So the interactions will occur as the system decides to serve ads as its actions, and the users will provide some feedback that the agents will observe. Whether or not the ad was useful will serve as either punishment or reward to improve the agent. The behavior that the agent learns is called a policy and is typically backed by a neural network. So the usages of reinforcement learning will span a large range. We've already talked briefly about ad placement and targeting, and this is already deployed in big production systems in Google, Facebook, and Alibaba. We can also look at the frontier of artificial intelligence to find recent successes in game playing, where DeepMind at Google has used reinforcement learning to push the state of the art. And reinforcement learning has even shown up in complex computer animations research for modeling human motions that are hard for humans to hand code. So the main takeaway is that reinforcement learning is an exciting emerging technology that has huge potential. So then the natural question is, at this point, how do we improve reinforcement learning? So recent trends in machine learning suggest us to take a look towards two different directions. One is increasing data, which in the context of reinforcement learning is increasing the number of interactions, and computation, which we need to scale out the increase of data. And hopefully, together, combining these two, we will improve the performance of your reinforcement learning algorithms. So now that we have reinforcement learning and we know that we need to scale out, let's walk through a quick example of how do you train a distributed reinforcement learning setup. So again, we'll go back to the example of a video prediction or ad placement system, and we have interactions with its users. The interaction will generate training data for the policy, which will decide which actions to take. And in many cases, you would want to do this in parallel, and in AI applications, oftentimes simulations are used here. All this data is then buffered and processed, and one would typically apply techniques such as data whitening and reinforcement learning techniques such as reward estimation to accelerate training. This clean data will now be used in the training process. And typically you might do something like SGD to train your neural network, and you will use multiple GPUs in order to accelerate the training. And finally, after the neural network is updated, we'll redeploy it as the new policy to interact with customers or users. And finally, you might want to run multiple replicas of these all at once as part of a distributed hyperparameter optimization process. So really, there's a lot of components going into a distributed reinforcement learning setup. And a natural question for you now is, how do we do this? What would you need to do this by yourself? So there's three components. First is hardware. And you might typically use CPUs or perhaps even GPUs if you want to accelerate your training. Next thing you want to have is a distributed execution environment to help you scale out. And finally, you want to have primitives for reinforcement learning that are easy to use and easy to program while being highly expressive. So let's first focus on the distributed execution environment. Standard execution environments such as Spark are inflexible for a lot of AI applications. This is because of the new requirements that these AI applications are demanding, which include extremely low latency, efficient data handling, and compatibility with different hardware resources. In the RISE lab, we developed Ray in order to support all of this. Ray provides a flexible set of abstractions, including task parallelism, an actor API, and data processing APIs. So let's quickly walk through what a typical Ray program looks like, specifically with using the task parallel API. So here we have two Python functions that we want to run asynchronously and in parallel. So first, we'll tag them with a ray.remote decorator, which turns them into remote functions. When these functions are invoked, they will execute eagerly and asynchronously while returning a future. These futures can also be passed into another remote function, which will execute asynchronously whenever its dependencies are ready. And you can call ray.get on any of these IDs, even though right now on the screen it only shows ID 3, and calling ray.get will retrieve the result of the call. And here's the computational graph equivalent of this small program placed on the side. So Ray also provides an actor API, which in Python is effectively a distributed class. So you see this counter class, for example, which has state in self.value. We can tag it with a remote decorator to turn it into a remote actor. Note that you can also specify a resource requirement, such as a GPU, which might be necessary when you're doing neural network training. When this actor is instantiated, Ray will start a process that holds the actor, and you can then invoke actor method calls. Again, similarly to tasks, when these actor methods are invoked, they'll execute asynchronously and eagerly while returning a future. So in the example on the screen, we increment the counter twice, and we can then call ray.get on the futures that each actor method returns. And at the end of the day, the actor method should return the values 1 and 2, which represent the stateful incrementation of the actor state. So now that you've seen the API, we can quickly dive into the Ray architecture. So we can start off with the node that has a driver process. On the same node, there will be worker processes that execute remote tasks and actors. The workers communicate data via an object store process, and tasks are scheduled on the workers via a local scheduler process. So then what happens when you want to scale up and you want to use multiple machines? Ray is able to scale seamlessly from one single node to the distributed setting. Other nodes will have pool of workers that will execute tasks spilled over from a single node, which is coordinated by the global scheduler. Data is handled across nodes via object store processes that communicate with each other. Finally, a control plane lives in the global control store. And this control store is backed by Redis and handles coordination among nodes. As a side note, you can run Ray in Spark by launching the Spark driver with the Ray driver, and also launching remote Ray nodes in Spark executors. As a side note, we've also built a variety of applications on top of the Ray API, including Tune, which is a distributed hyperparameter tuning tool, Ray SGD, which is a distributed SGD library, Ray on Pandas, Pandas on Ray, which is a data frame API, and RLLib, which is a scalable reinforcement learning library, which also will be the focus of the talk from here on out.
Thanks, Richard. So Richard has told you about Ray, which provides a task and actor API on top of hardware resources. And I'm going to talk about RLLib, which builds on top of the Ray API to provide abstractions for reinforcement and also a library of RL algorithms. So RLLib is actually composed of several components. First, we provide higher-level abstractions for reinforcement learning on top of the Ray low-level APIs. We provide a collection of state-of-the-art scalable RL algorithms. And finally, these abstractions can be used by developers to define their own algorithms very easily. So RLLib is really easy to get started with. If you just want to run benchmark task, you can run the RLLib train script. Here we're training a cart pull task, and we're running a very popular deep queue algorithm. So the cart pull task looks like this. The basic idea is you have a pull that's being balanced on a cart, and you want to learn a controller that can balance the pull by either moving the cart left or right. And you want to keep the pull balanced for as long as possible. And also you know where our logo comes from. So RLLib also has a very simple Python API. You can import these agents, and then you can specify custom environments. So these environments can be standard benchmark environments, or they can be environments that interact with, for example, web serving systems or with offline data logs. And you create an agent, and then to optimize the policy for this environment, you can call train, which executes a round of optimization using RLLib. So RLLib scales efficiently to multi-core nodes and also to clusters. So within a single node, we leverage optimizations such as vectorization to batch policy evaluations on GPUs and also on CPUs. So you can see here, increasing the batch size substantially increases single core throughput in both the GPU and CPU benchmark. RLLib also seamlessly scales to a cluster. So here we're showing the kind of the policy evaluation backbone of RLLib scaling nearly linearly from 1 to 128 cores. RLLib is also a unified framework for many scalable RL algorithms. So that's considered PPO, which is a state-of-the-art RL algorithm for high-dimensional control. We compare our scaling of RLLib against an MPI-based implementation up to 500 cores, and we're able to achieve faster performance. An RLLib implementation of evolution strategies, which is a evolutionary algorithm that can be more efficient than PPO, scales up to 8,000 cores, and we also scale much further than a Redis-based implementation. We're also able to implement distributed variants of DeepQN and DDPG using RLLib. And all of this is within one framework without needing to use specialized distributed systems for each. So RLLib offers a wide and growing range of RL algorithms, and many of these are actually contributed by the community. In particular, we're working with the Alibaba AI platform team to implement Impala, which is a recent algorithm released by DeepMind that achieves much better performance in many tasks. And RLLib also provides a collection of policy optimizers, so you can choose how to improve your policy. And all of these policy optimizers can operate at low scale and also scale up to clusters. RLLib also, beyond providing a collection of algorithms, makes it easy to develop new algorithms. So if you're an RL developer, to create a new algorithm, you need to specify a policy, some post-processor for the data produced by your policy, and then finally a loss function to improve your policy given the data. So this policy is typically a neural network defined in your favorite deep learning framework, for example, TensorFlow or PyTorch. The post-processor is kind of an arbitrary Python function. And your loss is also defined in your deep learning framework. And to get all this to work with RLLib, you have to wrap it into a RLLib policy graph class, which just holds these functions and the state of the policy. And then you can scale it with RLLib. In a nutshell, RLLib helps you define your learning algorithm with many utility functions. And also, once you've defined your algorithm, lets you scale it easily to a cluster. So let's look at how RLLib actually scales algorithms. So here you see a policy graph class that we've introduced before. And RLLib also provides policy optimizers, which execute a distributed training. So here both of these Python classes are sitting within the same Ray actor. But we can also create multiple actors in the cluster. Here are 4 policy evaluator actors, each of which holds a replica of the policy graph neural network. And the role of the policy optimizer is to execute the distributed communication to improve the policy. So depending on the strategy for optimization, this might include exchanging experiences across the network, or perhaps gradients of the neural network, or neural network weights. And to provide some insight on how these RL algorithms work, in both kind of a very simple setting and also the distributed setting, I'm going to walk through two simple examples in RLLib. So first is policy gradient, which is an RL algorithm that can be implemented in just a couple lines of code. And then second is the Ape-X distributed prioritization algorithm, which is a very simple idea around prioritizing experiences that you haven't seen before, but it can be kind of tricky to implement in a distributed environment. So let's look at policy gradient. And for this example, we'll use the cart pull task we've seen before. The goal is to balance the pull. So how do you define the policy network? Here we're going to use TensorFlow. So we're going to create a fully connected network of 2 hidden layers, and that has 2 output units. We take those 2 outputs and squash them into a probability distribution that says what probability I should move the cart left and right. And of course, you need to actually sample an actual action from that distribution. So how do you use this policy? Well, given an environment, here's the cart pull environment, you can get the current state of that cart pull environment, which includes the position of the cart and the angle of the pull. And you can use TensorFlow to run that action in an environment by calling environment.step, and the environment gives you back what happened next, the reward, which measures how good that action was, and then whether maybe if the episode terminates, it tells you if that happened. So this produces, if you do this a bunch of times, you get a bunch of experience data. So this looks like this. You have the observation, the action taken, the next observation, reward, and then you end up with all of this. So you have a batch of experiences for training. Okay, so the next step is to post-process this. And here we do a very simple post-processing step. We're applying temporal discounting. So all this is doing is propagating the consequences of your actions over time. So not only do we want to take into account the immediate effect of an action, we want to take into account long-term effects. So here, the first action moving left, we got 1 reward, but it led to the pull falling off the cart in 2 steps. So we need to back propagate that negative reward through time. And if it led to a positive reward, we'd also propagate that. And finally, we need to define the loss function. And there are many ways to do this. But for policy gradient, this basically amounts to telling TensorFlow you want to increase the probability of good actions. And once you define the loss function, you can use a gradient descent to improve the policy towards that objective. So how do you integrate this with RLLib? So previously we defined a bunch of snippets of code. We need to package into a policy graph class, and this is pretty straightforward. You take that code, you put it into this class, and you define the post-processing method. So now you have a policy graph. So given that policy graph, you need to set up distributed workers. So here we're creating 10 policy evaluation actors, targeting the cart pull environment as before, and the policy gradient graph we just wrote. So these are the 10 actors in our cluster. We need to choose our policy optimizer. Here we're going to choose a simple asynchronous optimizer that is going to compute gradients on the remote actors and send them back to the central driver. And then to actually train our policy, we just need to, in a loop, call optimizer.step. And each step executes a round of distributed communication. And between steps, we can also print training statistics, things like that. Okay, let's look at a more complicated example. So Ape-X is, the idea there is to prioritize important experiences. So you have a bunch of experiences coming from maybe simulation or coming from the real world. You put them in a history buffer, and you tag each experience tuple with a priority. And the priority could be determined in different ways, but the general idea is this experience important? Is it something you've seen many times before, or is it something novel? If it's something that you've seen a lot of times before, you don't necessarily need to train on it. You can just throw it away. But if it's high priority, you want to send that as soon as possible to your policy, so your policy can improve as fast as possible. So let's translate this into the distributed environment. we start with some existing policy. Here, the deep Q networks RL policy, and we create an Ape-X policy optimizers. So this is one actor in the algorithm. There's also other distributed components, such as the policy of evaluators we've seen previously that hold replicas of the weights, and also replay buffer shards. So these are actors holding the experiences in memory and the priorities. So during execution, the optimizer is sending the latest policy weights to those evaluators. The evaluators are sending samples to those replay buffers, and the replay buffers are sending high priority samples to the optimizer to learn from, and the optimizer sends priorities back. Now, in a call to optimizer.step, all this is happening in parallel and concurrently. So one call to step might execute tens of thousands of tasks over a course of just several seconds. And this is where a framework like Ray really comes in, where you can support really extremely low latency tasks at very high throughputs. And it scales really well. We're actually able to scale better than a reference implementation from the original Ape-X paper. And all this was written in just less than 200 lines of Python. Like, there's no cluster management. It's just Ray actors. So in summary, RLLib is a scalable framework for reinforcement learning. We're continuing to improve RLLib, and you can find us at github.com/rayproject/ray. So thank you. Are there any questions?
Yeah, if you have questions, you can walk up. Or
So I think Google does the network architecture search using RL, and they had some scaling issues as the network model was larger. How does RLLib or Ray helps there to scale that better?
The question was the question, how do you do search over different types of neural network models? Yeah. So RLLib doesn't help with architecture search and models, but there are other Ray libraries, such as a hyperparameter optimization package that can be used for that.
if no other questions, let's give one. Oh.
This is more of a question about reinforcement learning in general. If you have a situation where you can't run simulations, you have some real data episodes that you're trying to train over, what is a way of handling a reinforcement learning algorithm in a situation where you can't just run generate a simulation?
Yeah. So the question was, how do you handle a case where you don't have a simulator available? So there's a couple options there. So many of these RL algorithms can actually operate on offline data. So if you have web logs or things like that, you can potentially learn from those experiences as well. And so currently RLLib, you can put a custom environment, and that environment can interface with grabbing data from, for example, serving systems or offline logs. And we're kind of trying to improve the API there as well.
Anyone else? Eric, why don't you give an example? Oh, there's one. Why don't you give an example of what kind of enterprises are, what kind of enterprise use cases are being done on Ray?
Sure. So one of the companies using Ray is Ant Financial. They're a financial corporation, and they use Ray for many purposes, such as they're experimenting with RL and I think graph use cases. Yeah.
So you mentioned you run the Ray on Spark, but Spark is a synchronous framework. How do you run asynchronous tasks on Spark?
Yeah. So the question was, how does Ray run on Spark when Spark is bulk synchronous? And the answer is it's kind of a hack. You can start Ray inside Spark, and then after those tasks have started, they can kind of communicate out of band, not through Spark's object store, but through Ray's own object store. And you can also run Ray outside of Spark, but yeah, they're kind of separate.
All right. I think if you have any further questions, you can find Eric during lunch or later on. Give a last round of applause for him. It's great. It was a great talk.